Good morning, everyone. My name is Zavesra, and today I'll be discussing a very exciting and critical topic in material sciences and engineering. This presentation is a part of AAT Tech Talk series, and it is from the subject engineering chemistry. Today we are going to discuss about microwave characterization of materials during corrosion, its applications, and wireless sensor. Corrosion is a major problem in industries such as aerospace, construction, oil and gas, and transportation, causing billions of dollars in losses every year. Traditional corrosion detection methods can be slow, invasive, or costly. Today we'll explore how microwave signal interacts with material, how corrosion alerts electromagnetic properties, and how wireless microwave sensors help detect corrosion in real time. The innovation approach has the potential to revolutionize corrosion monitoring, making it more efficient, cost effective, and non invasive. Let's dive in. Fundamentals of microwave based material characterization. Before we understand how microwaves help in corrosion detection, let's first understand some key electromagnetic properties of material. Dielectric constant. It measures a material's ability to store electrical energy. It depends on the material's molecular structure and polarization. For example, water has very high electric density because it stores energy well, while metals have very low dielectric constant. Then we have magnetic permeability. This property tells us how easily a material can be magnetized. It depends on material's internal structure and responds to magnetic field. For example, electromagnetic materials like iron will have very high permeability, while non-magnetic materials such as plastic have very low permeability. Conductivity. This describes how well an material conducts electricity. It depends on the presence of free electrons. Uh, uh, for example, copper is highly conductive, whereas rust, such as iron oxide, is very less conductive. When a material undergoes corrosion, all these properties change, and that's where microwaves come in. They can detect these changes without physically damaging material. Understanding corrosion mechanisms and their impact. Corrosion is a natural electrochemical process where metal degrade over time due to environmental exposure. This environmental exposure can include oxidation, pitting, corrosion, intertriangular corrosion. What is oxidation? This is the most common form of corrosion. It occurs when a metal reacts with oxygen and moisture, forming an oxide layer like rust on iron. This oxide layer changes the material conductivity and dielectric properties, which can be detected using microwaves. Pitting corrosion. This is localized form of corrosion, creating small holes or pits in the material. Pitting can weaken the material much faster than uniform corrosion, and it is very dangerous if it happens in pipelines or aircraft components. Intertriangular corrosion. This type of corrosion where grain boundaries in material affecting their structural integrity, common in stainless steels and when exposed to harsh environments. Each of this corrosion mechanism affects a material's electromagnetic property, making microwave sensing a powerful tool for detecting them. Electromagnetic properties affected by corrosion. As corrosion progresses, it alters key electromagnetic properties such as conductivity decreases, dielectric constant changes, magnetic permeability changes, and let's see how it happens. So, in conductivity, when the conductivity decreases, the corroded metal becomes less conductive due to formation of oxides. Dielectric constant changes. The new oxide layer has a different dielectric constant than the original metal, affecting how metal interacts in electric fields. Magnetic permeability changes. Some oxides, like iron oxide, after magnetic property, make it possible to detect corrosion using microwave sensors. Microwave sensors take advantages of these changes to monitor corrosion in real time. Design principle of wireless corrosion sensors. Now that we have understood the basics how wireless microwaves corrosion sensors work, Let's understand what microwave sensors consists of. So there's a microwave transceiver, antenna design, signal processing unit, wireless data transmission. These are all the components of microwave corrosion sensors. Uh, what is micro transceiver? Sends and receives microwave signals interacting with the corroding material. Antenna design optimize the maximum signal efficiency. Corroding, which the considering the material's properties and environmental condition. Signal processing unit analyzes the received signal to detect the subtle changes in electromagnetic properties. Wireless data transmission sends real-time corrosion data to remove monitoring station. These components work together to provide continuous real-time monitoring without physically touching or damaging the material. Experimental setup and measurement methodology. To ensure accurate corrosion monitoring, structured experiment is conducted. Sample preparation. We take sample preparation in consideration, microwave measurement, data acquisition. What is sample preparation? A metal sample is exposed to a controlled corrosive environment, which is what can be a corrosive environment, for example, salt, spray, moisture. Microwave measurement. A microwave transceiver transmits signals, and their interaction with the sample is recorded. Changes, the sample is recorded. For example, changes in dielectric constant, permeability, and conductivity are tracked over time. Data acquisition. The recorded data is analyzed to determine how corrosion is progressing. The details are compared with traditional corrosion detection method for accuracy. Let's take a next slide is about a case study. Let's take a real-time monitoring of metal corrosion. So let's take a real world example. A wireless microwave sensor is attached to metal pipeline to track the corrosion. As the corrosion progresses, the metal conductivity and dielectric constant changes. The sensor detects these changes and sends real-time alerts to a monitoring station. If corrosion exceeds a predefined safety threshold, maintenance terms are alerted. So the accuracy of this real-time monitoring of metal corrosion is that it shows that the microwave sensors can achieve up to 90% accuracy, making them highly reliable tool for corrosion monitoring. We can see the advantages and limitations of microwave based sensing. What are advantages? It is non-invasive, non-destructive, real-time data, and remote monitoring. What is non-invasive and non-destructive? Unlike traditional methods, microwave sensors do not damage the material, so it's non-destructive. And it also comes in non-invasive property. Real-time data, it enables continuous monitoring without manual interruption. So you get a continuous monitoring with the data. So and remote monitoring, wireless capability allows corrosion detection to hard to reach location. So you can place a microwave sensor in very remote and isolated area, and it will send you it has the capability to detect corrosions in very hard to reach location, but it comes with limitation. So there is interference issue, early stage detection sensitivity, and complex signal processing. What is interference issues? So external electromagnetic signals can actually affect the measurement. So as we studied, it has component which is electromagnetic signals, and if we get external electromagnetic signal, it can actually uh, affect our actual measurements, the real-time measurements. Early stage detection sensitivity. Microwave sensors may not detect early stage of corrosions because it is very faint. Complex signal data processing, which requires very high data analysis techniques, and these are the limitations of the microwave sensing. Despite these challenges, there's an ongoing research which aims to improve sensor sensitivity and accuracy. Future application. Microwave based corrosion sensing is set to transform industries. For these industries include infrastructure monitoring, aerospace engineering, biomedical application. For infrastructure monitoring can include bridges, pipelines, industrial structures. Aerospace engineering can include aircraft structural and health monitoring. Biomedical application as biomedical engineering is drastically increasing, monitoring corrosion in medical implants and devices. Future research will focus on developing more sensitive and miniaturized sensors, AI driven data analysis for better accuracy, and expanding applications to new material and environments. Conclusion and takeaways from this presentation. Microwave sensors provide non-destructive real-time corrosion monitoring. Corrosion alters the conductivity, dielectric, constant, and magnetic properties, which can be detected using microwaves. Wireless sensing offer a cost-effective and efficient alternative to traditional corrosion detection method. Thank you all for your attention. I'd be happy to take questions.